All right. So that's with the homework. Make sure that if you are doing pictures, same thing, file, insert file. All right, insert image. So quiz number two came out really well. Just had a couple people with the class width doing that a little bit incorrectly. You'll still see it again. I think I have one of those on the final exam. But finding the class width, you round up. So some people, I think the class width was, when you calculate it, was 5.3 or something like that. You got to round up to 6, okay, on quiz number 2. So I think the class width was like 6, okay. So when you round up, you get a whole number. Some people round down, and then finding the classes. Each class, some people did like 11 classes when there were only 5 classes. Okay, so I try to give you feedback as much as I can, and the reason why I do that, and it hopefully sends you an email if you have your notifications on in your email. I do a lot of with email. You can tell by now. You know, like, hey, there was no class Monday. So that was a really important email. Anybody come yesterday to school and be like, oh, there's no one here in the parking lot? Okay, so good, you checked your email. All right. Yeah, so that kind of threw a kink in some things, but email, I'm emailing all the time, so check your email. I got a lot of emails from students, so that's really useful too. But quiz number 2, I give feedback in the quiz, and then you should go back and check and see where you made your mistake. Don't just be like, oh, I got a 12 out of 15. Cool. That's pretty good. All right. That's the best quiz I've ever had. Or something like that. I was being sarcastic. Okay. But go back and check, see why you lost 3 points, or same thing on the test. Okay. When I grade the test, the last question was 11 points. So same thing on the last question. I just type out something real quick, feedback on the last question in case you made a mistake on something with class width. If you still don't know why you lost points, just reply, look at your test and you got 6 out of 11 and you still don't know why you lost points on that last question, 28, then you should be able to check that and write in the feedback to me, and then I'll see that. I'll get an email that says you had a message there for the quiz. All right, test. So I'm going to show the test up here. Just a real quick on the test. First of all, were there any questions on any of the multiple choice portion of the test? I'm really just going to get to the free response. Most tests. So some quizzes, like quiz number 1 was all multiple choice. Quiz number 2 was all free response because you need to draw graphs. Okay, that's kind of hard to do with multiple choice. So sometimes this quiz is all multiple choice, all free response. Sometimes tests are both or one or the other. Okay, so I want to make sure that if you have any questions about the quiz, please let me know, or the multiple choice on the test, please let me know. Here we go. Is it up? There we go. All right, so the last question, again, free response, 5 points for same thing. It's like almost exactly identical to quiz number 2. Okay, so there's no surprises here. I'm not gonna throw something on this test or on the quiz that you like, I never saw that in homework before. Just a little bit different style. And I laid out what I wanted there, and that's exactly how I did the warm-up problem on Wednesday. That's how quiz number 2 was. Find the classes. Again, it says 5 classes right there. And the numbers are in thousands of dollars. On your calculator, find the mean, sample standard deviation, and median. So right here, a lot of people did sample standard deviation by hand. They did correctly too. So I want to make sure when you're doing sample standard deviation, especially when it comes down to a decimal, like some people said, oh, it's 18 or it's 20. Some people rounded quite a bit. When you're finding these numbers like mean and standard deviation, you usually want to round to the nearest hundredth of a decimal place. So I think 18.2, I accepted both of those. That was really useful. Finding the mean and standard deviation. The median was 25. The mean was 20, I think. Something like that. So it was a little skewed left of the data. One thing I asked for, going back to the quiz, was unusual points. Are there any outliers? I didn't ask you for that here just because it's not really that important, but if the numbers are far outside the data set, that's an outlier. I didn't ask that. Histogram, so you want to make sure your histogram matches your classes. Okay, so your frequency, I think it was 74033, something like that. 74033 were the counts for the frequencies. So you just draw that in your histogram. So that was pretty straightforward. So if you're having trouble with histogram, again, please let me know. And I'll go through how to draw a histogram with you. We'll sit down one-on-one. We can do a Zoom if you need to, or during our downtime. Just tell me, hey, I don't know how to do histogram. Anyways, how do you insert your stuff here? Because this you have to do by hand pretty much. I've had students do this, type it out, right? You could type in, first class, 11 through 21, right? Second class, 22 through 33. You could type it out and do each of those, but inserting the file. So like I said, inserting, I keep using that word insert because the insert button is right here, okay? If you insert a image, the image is going to go straight into here. If you insert a file, then that's an attachment, okay? So I want to insert an image. There's two ways to do it. I could do it here, upload image, or I could do it over here with the 3 bars. Usually if I have a bigger screen, I just go to the little image button, which is right there, and it asks me to upload the image. I just click on that, and it's going to look through your computer over here, your computer files. Very similar if you have a Mac. So I'm going to look in pictures. I have some pictures in here. So I just open it, and it asks me, is that what you want as the image? So then I'm going to insert. It won't let me insert. The button's down there. Come on, button. The button was down at the bottom, but it was covered with the student view. Okay, so I'd have to click on the insert image. Same thing, exactly the same for homework. Okay, so your picture should pop up in there. The button's down here in blue. I can't get to it unless I leave student view. Oh, it worked. Okay, there we go. So I just took a picture of the problem. I screenshotted the actual problem, and I inserted it as a picture. So it's called a PNG file. You can do JPEGs. So a lot of people are taking picture of their homework. And it's so again, this is a picture. With a Mac, I think it's Windows Shift 4 to do screenshots. With a PC computer, you just go to the snipping tool and snip. Do you guys know how to do that? Snip, use the snipping tool. You just type it in there, snipping tool. With pictures, again, you just want to save the picture as a file on your computer. Anybody use the Canvas app on their phone? Okay, we got a few head nodders. Okay, was it pretty easy? Okay, Canvas app is really easy. It's really easy to grade as well. You just get the Canvas app on your phone, Canvas for students, and you just take a picture and you click upload into here, right? So you do the same thing, but your picture's already on your phone, so it just searches your phone for the picture, and you just insert it in there, just like an email or text message. Cool. Spend a lot of time with that. All right. Any other questions about anything at all? Yeah.
I tried doing the screenshot method that you just mentioned, and
Mhm.
what is it? It would, for some reason, even if the image was correct, it would be automatically marked as wrong.
Oh, really?
At least for me. So I don't know
Okay.
if that's, I don't know if that's from.
You did it on a computer?
Yeah.
Okay. So sometimes, and a few people have this problem with the homework when you're inserting, and I had this problem during COVID times with Wi-Fi. So I had to upgrade my Wi-Fi router, and then it worked fine. So sometimes the Wi-Fi issue, it says that it did not insert, and I had a couple people do this with the test. On the test, they said I inserted the file, and they ended up emailing it to me. I'm like, oh, your file attached. Okay, so it was in there. But yeah, sometimes it'll say corrupt file. Sometimes like this, the PNG. Sometimes it doesn't accept certain file types. So there's other file types. I think I have most of them acceptable on here. I think I said most file types or something like that, but there's some file types that are unacceptable in Canvas. Also, it could be a browser. Google Chrome and Firefox are usually the best. So if you're using Edge or any of the other browsers, sometimes that's an issue as well. And they're not compatible with Canvas. Yeah. Okay. Okay, yeah, I'll look for it. Okay, thanks for letting me know. I'll give myself a note here. Okay. Okay. Oh, that's another thing. When you're doing homework, the homework, I'm looking for the assignment and the page number. There we go. So when you do your homework, don't just write the page or just don't write out all the problems, but say, oh, this is homework 3.1, and then it's a title, 3.1, page 140, and that's 2 through 50 even. Okay, that's at the top, and then problem 2. Okay, and you're gonna write what problem 2 is. Okay, then problem 3. So this is the title, because some people will just go 2 through 50 even, and then the next line it starts off again with problem number 2, but there's no title. So I'm looking for this when I'm grading homework. Okay, and then I'm checking to see which you have in there. I'm not really a crazy stickler. I mostly grade on completeness, but if you're just copying homework answers, I can see that as well. Okay, so showing your work is really important. Just like in any other math class. But if you're just writing, you're just writing a decimal answer, like I want to know how you got that answer. Okay, so you want to say, oh, I used the calculator, or I used stat calc one variable stats. That's how I got the mean and the median. Well, you didn't have to do it on the test because I asked you to use your calculator, but on a lot of problems, you could do it by hand, or you could do it on the calculator, or you could look up the answer, which some people do. Okay, so I'm trying to avoid that situation. Anyways, that's titling. So that's really helpful when you do that stuff. So it's easier for me to find. All right, so we're at 3.1. Today is going to be pretty crazy. We got chapter 3, 3.1, 3.2, 3.3. There's a 3.4, which is a little more straightforward, but probability of chapter 3 is probability. This is where some people do okay in chapter 1 and 2, and they're like, oh, I got stats. And then chapter 3 comes and it's like a big shocker. So it takes a while for some of the ideas to sink in. It becomes a little difficult. There's a lot of mathematics involved in calculating probabilities. You can multiply probabilities together. You can divide probabilities. I'm trying to simplify as much as possible. But a lot of people tend to struggle, just letting you know, with chapter 3. Then chapter 4 is like, oh, okay, this makes sense. Okay. Chapter 4 is still probability, but we use tables and stuff like that in chapter 4. But chapter 3 is a lot to digest in one day. So I hope that you follow along, and if you need to, I'm recording so you can check out the video on the next day. Anyways, chapter 3.1. It's just an introduction to probability and probability rules. So one of the things that we want to look for in probability is almost always a decimal. Sometimes they give you a percent. Sometimes you have a percentage. Sometimes you have a decimal. I'm not too concerned about the percentage, but all the answers in the back of the book, they'll have decimals. Okay. Unless the problem says, find this number as a percent. So going from a percent to a decimal is really important to know. I normally don't spend time with this, but a lot of students get confused with how to do this. I could go from a percent to a decimal, or a decimal to a percent. I go from percent to decimal or decimal to percent. Okay, so it has to do with the decimal place. So if I have a number like 30%, this is not in the book, by the way, 30% as a decimal. Okay, what am I going to do? I'm going to need to do move the decimal to the left. I'm going to move from a percent to a decimal. I'm going to move the decimal to the left, 0.30. From a decimal to a percent, 0.41 to a percent, I'm going to move the decimal to the right, 41%. Okay. That's all cool, fine and dandy. A lot of students get confused with that. Percents and decimals are always a number between 0 and 1. Okay, so when you have a percent, this is the notation that we use, a proportion or a percentage. A proportion is always between 0 and 1. So here's the notation. The notation looks like this: 0 less than or equal to probability, and usually we use P of X. Okay, so like they say, prescription drug companies, they mark up their drugs by 2,000%. Okay, 2,000% is not a portion. Okay, 2,000 times the actual price that they get it for is what they sell it for. So the markup, okay, that's not necessarily a percentage or a proportion. A proportion is considered a part of a whole. Okay, so if we have 1, notice equals 1. So if you're at 100%, that's guaranteed to happen. If you're at 0%, that's guaranteed not to happen. So like rolling a die. If I roll a die, I'm going to use dice and cards today. So we'll get familiar with that. Flipping a coin, we'll get familiar with flipping coins. If you roll a die, what's the probability of rolling a 2? Let me write it out. Rolling a 2. Okay, I usually write my numbers as fractions. Fractions become decimals, which then can become percents. Okay, so there's 1, 2 on a die. There's 1 divided by 6. Okay. So this is the probability of rolling 2. I can convert that pretty quickly on my calculator. 0.167, which is 16.7%. So this is called notation. Most of the time in math world, people see parentheses and they're like, oh, that means multiply. Okay, not here. This is just called notation. This is a probability of an event occurring. So the actual definition of probability. So probability, we use the word, this is the definition, the chance. So we use the word chance. The probability, the chance an event will occur. So we got that word chance. What are the chances that it's going to rain tomorrow? Like 0. You live in Santa Maria, 0% chance of rain. That means it's not going to happen. Okay. If it's a 20% chance of rain, possibility, we might have a thunderstorm. Okay. So we have the chance of an event occurring. And then the notation, which I just showed right there, I put the event in the parentheses, probability the event occurs, equals the number of successes divided by total successes. What's a success? That means a victory. You might see the word outcomes as well. The number of outcomes divided by total outcomes. So I use the word success. In this case, if I roll a 2, rolling a 2 is a success. There's 1 success. There's 6 total possibilities. There's 6 total outcomes. So that's kind of a definition of probability in words and symbols. Okay, probability in words and symbols. If we have cards, so like I mentioned, we're going to use cards quite a bit. Probability of getting a king in a deck of cards. So there are 4 of each card type in a deck of cards. And there's 52 total cards in a deck of cards. And I'm going to write that as a decimal. I forget what the decimal is. I think it's like 6% or something like that. So I'm happy with fractions. For example, on quiz number 3, we're going to take. If you write your answer as a fraction, I'm happy with that. Okay, you can just leave your answer as a fraction as well. A lot of people will simplify that. Oh, that's 1 divided by 12. Well, you got it wrong because the answer is 1 divided by 13. So if you simplify, a lot of people make mistakes. So just take 4 and divide by 52. 0.078. Okay, so we give you, I like fractions or decimals. Percents, not so important. Percents are not very important. Because when we're going to do math, we're going to multiply proportions together. We're going to add proportions together. We're going to subtract proportions from each other. And there's actually dividing proportions by each other. All right, so I'm going to talk about coins here for a second. There's dice, here's cards. How about coins? So when I flip a coin, you get heads or tails. Probability of getting, I'll write down here, probability of getting heads is 1/2. There's 1 head on a card, on a penny or a quarter, which is 0.5, 50% chance of getting heads. So if I have a coin, that's the probability of getting 1 head. What if I flip 2 coins? What's the probability of getting 1 heads? Okay. What's the probability of getting 0 heads when I flip 2 coins? There's no heads at all. It's kind of hard to imagine, but the answer is 0.25. Okay. There's a 25% chance of getting 1 heads flipping 2 coins. It seems like it would be a 50%. But I need a picture, I need a visual image in order to make this happen. And the visual is that we're going to use is called a tree diagram. The tree diagram, there's a tree and there's branches in the tree. So the tree diagram helps us find the probabilities. Just gives me a picture of what this looks like, the events occurring. So I'm going to split. Your tree diagram always splits. In the book, they use like, it goes down, over, and down like that. So they do it a little bit differently, but you'll see it. There's actually a tree diagram. There's a couple tree diagrams. There's one on page 130, one on page 132. I like the one on page 132. If you're taking a look, that is this. Do you see what I mean by it goes down and it goes straight across? It goes down. This is probability of driving a Ford, GM, or Honda, a compact or a midsize, and a color. So they have a bunch of colors there. So find the probability of driving a white Ford midsize. That's 1 out of, looks like 32. Okay, 1 divided by 32. So find the probability. My question here is find the probability of getting 1 heads with 2 coins. Well, how am I going to do that? I need to count how many successes there are and divide by the total number of successes. So if I flip this branch right here represents 1 toss. So this is my first toss. Heads, tails. I want to flip the coin again. So let's say I flip a coin and I get heads. Then I flip another coin and I get heads again. That's going to be this branch. Or I could get tails. If I flip the first coin is heads, second coin is tails. So this represents heads on the first coin. This represents heads on the second coin. heads first coin, tails second coin. Or I could have flipped tails first. Okay, get tails or heads. And right here, this is the total outcomes. Okay, there's each of these branches represents 4 total outcomes. So I have, how many ways can I get one heads with exactly, when I write that, I mean exactly one heads. I'm gonna get exactly one heads. Okay. Getting 2 heads is one, there's one way to do that out of 4. Getting 1 heads, there heads tails and tails heads. I guess I should wrote HT because HT came first. Heads tails and tails heads. There's one way to get. All right, 1 heads. There's 2 ways that happens. So that total number of outcomes is 4. And there's 2 ways that can happen. So that's 0.5. So 50% chance of getting 1 heads and 2 tosses. Okay. There's a 25% chance of getting 2 heads and 2 tosses. How about tails? Well, tails is exactly the same. What's probably getting 2 tails? There's one way to do that out of 4 outcomes. I'm gonna switch this. I don't like that right now. Heads, tails, heads, tails. Be consistent. Come on. All right, there we go. That's 2 tosses. What if I have 1 coin and I toss it twice? It's the exact same tree diagram. The same result would come out. Okay. How about I'm going to do 3 tosses now. So now I'm going to put another branch on here. Now I have 3 coins, or 1 coin flipped 3 times. Getting real compact down there now. Heads, tails, heads, tails, heads, tails. So find the probability of getting, we can answer all kinds of questions with the tree diagram on the probability of getting 3 heads with 3 coins. So I got to figure out the total number of outcomes. The total number of outcomes is 8. Okay, that's kind of weird, right? 3 coins. A lot of people are like, oh, 3 coins, flip it twice, that's like 6 outcomes. Well, it's not, okay? Because heads, tails, heads, tails, heads, tails, heads, tails. There's 8 total outcomes there. And how many different ways can I get 3 heads? There's only one way that can happen. That's 1 out of 8. 1 divided by 8. Okay.
And when you put 2 coins, 3 coins, you're talking about tosses, right?
Yeah,
One
tosses.
coin.
Yeah.
Okay.
So 1 coin flipped 3 times, or 3 separate coins. I could flip 3 coins. And then I could have what's probability of all 3 of them being heads.
Oh, okay.
It's still 1 out of 8.
Okay.
Yeah, good question. The tree diagram is representative of the number of outcomes. I got the total number of successes. There's 1. And sorry, number of successes is 1. The total successes is 8. There's 8 total on there. Okay. There's a shortcut to find the total though, this total right here. And this is called the fundamental counting principle. And it's on page 132 as well. The definition on 132 is called fundamental counting principle. All you're gonna do is multiply. So we're gonna take, it's kind of weird how they write it. It says they use letters, they use M times N. So you just multiply. You just multiply the total outcomes of each event. That'll give you your total events. So there's 2 ways for this to occur here. There's 2 ways for this to occur, and there's 2 ways for this to occur. So if I multiply 2 times 2 times 2, I get 8. Using the fundamental counting principle, just multiply. Okay. The example in the book, page 132. If you're not there, they say find the probability of getting a car. You have 3 types of manufacturers: Ford, GM, and Honda. I'll show this in case you don't have your book handy. Ford, GM, and Honda. You have compact and mid-sized cars. And then there's white, red, black, and green. 1, 2, 3, 4. So again, find the probability of getting a mid-sized Ford that's white. What are the chances of that happening? Well, in order to find the total number of outcomes, instead of doing a big old tree diagram like they did down here, see the tree diagram, and then counting, I got to count all those. Well, no, I can multiply 2 times 2 times 4. Oh, there's 16 total outcomes. That makes sense? 16 total outcomes. What's probability of getting one of those? A white Ford midsize. There's one of those. So it's 1 out of 16. 1 out of 16. And whatever that decimal is. So that's using the fundamental counting principle. I just multiply things together. I could use this idea, this fundamental counting principle. That's the tree diagram. I can use the fundamental counting principle in a couple different ways. I'll get to that in a sec, but I just want to talk about the outcomes and the sample space right now. So with this, I made a tree diagram. It's a good picture of what's happening with these probability rules. What I'm going to do, I'm going to use the same problem, but I'm going to do it differently. Okay, it's like copy and paste in Microsoft Word, right? You can have multiple ways to do the same thing. So I'm going to do the same thing here, but I'm going to use what's called the sample space. The sample space lists all possible outcomes. So I could do a tree diagram, or I could just list all the ways that these things could happen. So I'm going to use it's a capital S and a bracket. Okay, a little curly bracket, fancy style right there. So S equals what? What is the sample? S represents the sample space. And inside the bracket is going to be my total possible outcomes. So again, I'm flipping 3 coins. So the first outcome is heads, heads, heads. I can get 3 heads in a row. So I'm just going to list H as meaning heads. I don't need a key or anything. I'm going to put a comma there. The first 3 tosses are heads. Or I can get 2 heads and a tails. You can kind of brainstorm when you're doing the sample space. Heads, heads, tails. What's next? Heads, tails, heads. And what would be next? Heads, tails, heads, heads, tails, tails. So when my first toss is a heads, there's 4 outcomes. When my first toss is a tails, imagine I kept going on this. I'm just going to go on another row right here because I don't have enough space. If the first toss is tails, then I have 4 different outcomes as well. Tails, heads, heads, tails, heads, tails. And the order doesn't even matter at all. When you do this, there's no particular order. What's next? Tails, tails, heads, tails, tails, tails. Close the bracket. There's 8 total outcomes. There's 8 ways that I could do this. Find the probability of getting 3 heads. Well, I can see that there's only one way to do that. I'm going to use the definition now. There's only one way to do that, divided by 8 total outcomes, because I listed that there's 8. So that's another way to do the same thing, a tree diagram or a sample space. I could do the same thing. So the fundamental counting principle, I can apply this rule, like I did here, to any event. There's 2 different types of probabilities. There's classical probabilities, which are fixed sample spaces. So like tossing coins, pulling cards out of a deck, spinning a spinner, Like you guys ever play Twister? Have you heard of the Twister game? Spin a spinner. And there's 4 different colors and then red and then foot, right? So that's a closed sample space. So anything those are all called classical probabilities. Empirical probabilities are things that are predicted to happen over time. For example, the chances of rain. That's not a fixed sample space, right? I can't say, well, in the next 7 days, it's going to rain one of those days. So the probability of rain today is 1 out of 7. Empirical probabilities don't work that way. Okay, finding that there's a 20% chance of rain works a little bit differently. And actually, weather people, they gotta, study statistics. They use statistical models to predict what's going on with the weather, or they just watch the Weather Channel and then just repeat what they saw on the Weather Channel. That's a joke. Okay. Okay. So what I'm going to do is use fundamental accounting principle and find the number of ways to do something. So we use the same idea, and I'm going to talk about empirical probabilities because we can count the number of ways that certain things can occur using the fundamental accounting principle. So this is like having a phone number, right? Or a license plate frame, or an access code, or a combination lock on your the bicycle. You lock the bike up. How many different ways, how many different combinations could I make for my bike lock? Okay. So the fundamental accounting principle will give me the total number of outcomes. I usually use a box to represent this thing. So when I was a kid, I had a bicycle and it had a 3-number combination. And I locked my bike up. I was so excited. It was Christmas. I got the bike lock for my bicycle. I used to ride my bike to school every day. Kids don't do that anymore, do they? The thing of the past. So I locked my bike up the first day back to school after Christmas break. And I forgot the combination. It was 3 numbers. So I'm like, oh, what am I going to do? I don't know what to do. I had to leave my bike there, or I could just sit there and figure out what the combination was. I think it started with the 3. I think the first number was a 3. So I knew the first number was a 3. So there's 3 numbers. So I want to know how many different numbers did I try? Okay. How long did it take me? Did it take me 2 years to figure out what the combination was? It actually took me about 5 minutes because I sat there and tried different numbers, pulled the lock, tried different number, pulled the lock. So I started with 3 because I knew the first number was a 3. And then I had a number and a number. So the first number was a 3, but I forgot the other 2 numbers. So it's really important if the numbers repeat or if they do not repeat. If numbers repeat, then you got different number of total outcomes. First number is a 3. There's only one way that can occur. So here's the numbers. And then down here underneath, I'm going to put the outcomes. So the first number is a 3. There's only one way I can get a 3 right here. Times, I'm going to use the fundamental accounting principle. I'm going to multiply. There are 10 different possible numbers that came next. The last number, there are 10 different possible numbers that came last. So if I multiply all those together, I actually, in a 3-number combination lock, I only had 100 possible combinations that would have worked and opened the lock. Does that make sense? If the numbers repeat, for example, I could have had 3, 2, 3, could have been a possibility, right? If the numbers repeat. If the numbers do not repeat, then the results are a little bit different, okay? And we'll get to this in chapter 3, section 4. If the numbers do not repeat, then my number of outcomes, this is outcomes if there are no repeats. If the numbers could be the same. The outcomes, if the numbers are not the same, is going to be different. The first number, there's only one way to do that. There are now 9 numbers that could be here. I already used the 3, so there's only 9 numbers left. 0, 1, 2, 4, 5, 6, 7, 8, 9. There's only 9 numbers left. So let's say the combination is 3, 7, 4. So I used the 3 and the 4. for my second number. My last number, there's only 8 different numbers left. So now there were 100. If the numbers did not repeat, like let's say I knew, oh, the numbers don't repeat. Like, yeah, I really knew statistics when I was in 4th grade. I didn't know that. I just tried numbers until the bike lock opened. Okay. A lot less results. If the numbers do not repeat, there's less results. But this is how to calculate total outcomes. What's the probability of me guessing the number? 1 out of 72. So this number, using the fundamental counting principle, gives us the total successes. And typically, the number of successes, if there's only one way that the event can occur, then that's 1. 1 divided by the total. For the fundamental counting principle. What if there are 4 numbers? Let's just say there's 4 numbers. 1, 2. Each box represents a different number. If there's 4 numbers, have you ever driven in through a gated community? Okay, and they got a combination or a punch the buttons, right? It's like a telephone, the old telephone numbers. There's 10 numbers possible, but if there's 4 different numbers that are going to go here, the first number, there's 10 outcomes. And then there's 10 numbers. This is if numbers repeat. Numbers repeat. Did I do that wrong? Oh yeah. If numbers repeat, I put a no there. If they repeat, if they do not repeat, then I cannot repeat numbers. Okay. So 10 times 10 times 10 times 10, there's 1,000 total outcomes. So if you go to a gated community, you're like, okay, there's 1,000 ways that this could work. Right? Am I ever going to guess this code? And you usually get locked out after like 5 attempts or something like that, or 3 attempts. It locks. All right. And then you got 5 minutes, you got to wait. So there's 1,000 combination you can use to open up that gate in the gated community. Same thing with a combination lock. If numbers do not repeat, 10 times 9 times 8 times 7. So that's 10,000. This is 5,040. 5040. If numbers do not repeat, then I can cut it in half. So if I remember, okay, my uncle lives in a gated community. When I go over to that place, I can remember the numbers don't repeat. Okay? I got 5,000 possibilities to open up the gate. Still probably not going to happen. But here's the secret. On that gate, the numbers are all rubbed off. So it has a code on there. And it goes something like this. Because they don't ever change the code. And I remember that when I go in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 star pound. Okay, it looks like the telephone dial. Okay, so the numbers are rubbed off a little bit because people press the numbers so many times. So if I know that, there's 4 possible numbers. So if you look at it closely, you'll see that. My dad lives in a gated community also. He sold his house and bought a trailer. He lives in that trailer park over here on Taylor Street, off Taylor Street. They have a code as well, but the numbers are rubbed off. Okay, to get into the gate. So there's 4 different numbers that I could try. So if that's the case, I got 4 that go here and the numbers do not repeat. So I cut that down quite a bit. 1, 2, 3, 4 zeros, 10,000. All right. Oops, that's wrong. I did my math wrong. 24. Okay, if the numbers are rubbed off, now I know there's only 24 combinations, so I can sit there and guess. What if I know the first number? What if I know the first number? The first number is a 7. That's all I remember at my uncle's place next to McCoy. I can only remember the first number is a 7. McCoy next to Albertsons, I mean. They like a little gated thing right there. Are you laughing because you live there?
No, are you gonna give us the code since we go there?
Oh, I don't know. But I remember the first number is 7. That's all I remember. I got it in my phone and my notepad. So I don't have to pull up the phone. The first number is a 7. I'm very, very sure. 7. There's only one way that can happen. So look at, I cut it down to 6. I press 7 And then I know that the next three numbers are like, it's like 7683, 7863, 7368. I could just sit there and try it. Right? So pretty easy to get in if you got the probability down, figure it out. Or you just use the real trick is wait for someone to drive in and then follow them in there. Right? So that's what I did when I delivered pizza. I delivered pizza for a few years. Gated places, I just sit there out in front and wait for someone to drive in, drive right and follow them in. All right. Unless they stop and they park. Oh, you can't come in. So that's probabilities of combinations that you can use. License plate. Okay, with a license plate, number, letter, number. There's 7 digits on a license plate. So I can do the same probabilities here. How many different license plate possibilities are there in the state of California? You got to have 7. So this is for a license plate. So there's 7 different. I'm not going to write out exactly everything for a license plate, but it's going to be. I'm going to write it really small. First is a number, then there's letters. Then there's letter. Then there's letter. Number. I mean, you could do symbols and stuff like that because, you know, been what turn of century 1900, cars have been around. They started license plates in the 1910s or 20s when they started registering cars and DMV became a thing. So we got different license plates combinations that we can come up with. Let's figure out the total if letters and numbers are allowed to repeat. There are 10 numbers that can go first. It's rare to start with a 0 though. I could say in the book they go, the first number is an even number. So that would be 5. Okay, there's 5 even number, 5 odd number. They consider 0 an even number. Letter 26, 26, 26, 10, 10, 10. This is if numbers and letters are allowed to repeat. So if you just do that math, you're just punching buttons in the calculator. You can figure out the total number of outcomes. It's going to be a big, huge number. Big, huge number. Probability of the getting a certain license plate would be 1 out of the total number of outcomes. All right, the last thing that I like to talk about is the lottery. Anybody win the lottery in here? You wouldn't be here if you won the lottery? I don't know. I'm undecided. I got kids and I'm like, I should just like, you won the lottery?
I won $5 from.
Oh, $5. There we go. All right. So how many numbers did you get?
I think it was like 2.
You got 2 numbers out of 6, right? 2 out of 6. So how you get a payout? You got to guess the number, right? What number it's going to be. A lot of people think that the chances of winning are based on how many people play, but the amount of money is based on how many people play. The chances of winning do not change. So the lottery could be $3 million. That's like a 1-year salary if you're a professional athlete, right? Or not even a year. Now I think they gave Aaron Rodgers $50 million for 1 season to play football, and he only plays 16 games or something like that. That's pretty crazy. A lot of money. Anyways, lottery's not even close to that. But the probability of guessing a number, there's 6 numbers. So there's, I think, was it 75 numbers or something like that?
Yeah.
So there's numbers are 1 through 75. And there's 6 different outcomes. So we can figure out the probability of winning the lottery. It was a lottery. And they have Super Lotto, there's Powerball, there's so many lottos now. And do schools ever get the money? I don't know. I never was at a school. I've been a teacher for 20 years. I was a student for 12 years. And I never heard one time where someone was like, oh, we got these deaths from lottery money. It never happened. Lottery is supposed to go to the schools. Anyways, there are 75 different numbers. Numbers do not repeat in the lottery. 75 different numbers that can go here. 75, 74, 73. So if I multiply those numbers together, that'll tell me the probability of winning the lottery. 75 times 74 times 73 times 72 times 71 times 70. The Powerball, in fact, my calculator has E on there. We'll learn about scientific notation unless you already know what it is. It says 1.4 E11. Okay, 1.4 E11. So I'm just gonna call it 1 E raised to the 11th power. That just means move the decimal to the right 11 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Actually, I'll put that 4 on there. That makes it even bigger. All right, so there's a total outcomes. Okay, so this is the total successes of winning the lottery. If you buy one ticket, it's 1 divided by that. Oh, but you're gonna spend $20 because you think your chances increase for winning. So if you spend 20, let's just say $10. I'm gonna spend $10 on the Powerball, so that's gonna increase my chances, right? Or $100. Okay, you're gonna spend a lot of money. I've seen people do it. I worked in the grocery store as well. I used to sell lottery tickets for days, and I was like, that's the reason why I never played lottery. I saw these people come into the store and spend hundreds of dollars on lottery. They never win. And if they do win, they take the winnings and buy more lottery tickets. Okay, so this is 1 out of that 104 billion. Is that a billion? Yeah. If you write that as a decimal, if I do 1 divided by that, it's a little bit different outcomes, right? So if you're gonna, that's if you play $1. If you play $10, remove a 0. So instead of 1 out of 140 billion, it's 1 out of 14 billion. Okay. Oh, you just increased your chances a ton. 14 billion. Okay, that's probably not gonna happen either. Either you played $100. Let's say you had $1 million and you're gonna play lottery. Spend $1 million on a lottery ticket. Okay. Let's remove a couple of those zeros. It's still 1 out of 140,000. If 140,000 people had $1 million and they all put $1 million to play the lottery, there's probably still not going to win, right? One person probably would not win if they 140,000 billionaires spent $1 million. Probably still not going to happen. Okay. I can't even win a raffle where there's 200 people in it. You know, it's like, come on, that's not going to happen. 1 out of 200 chances, probably not going to happen. All right, that's pretty much covers. There's another definition. It's called complementary event. Okay, so this is the last definition that I'll give you. There's not much about complements, but a complementary event is 1 minus the probability of an event occurring. They use a symbol called E prime. So find the probability of being right-handed. Where I'm going to put this. I'm gonna run out of space. I'll put it over here. So if I say find the probability of being right-handed, so I'm just going to count the number of people and the number of people that are right-handed. So I need the total number of people. So let's say if there's 100 people, how many of them are right-handed? And it's usually about 90% of people are right-handed. It's usually, I mean, it's going to fluctuate year after year after year. Which hand do you use? The complement to that is the probability of being left-handed. Or in the book, they call this is called prime. This just means complement. This little symbol right here. That's just, it's like a little apostrophe right in there. The complement to being right-handed. Well, that's 1 minus probability of being right-handed. And you guessed it already. 1 minus 90. I'm doing some math now. 100 over 100 is like a waste of understanding. There we go. 10 out of 100, which is 0.1. Well, if that's 90, then this is 10. Okay, probability of being right-handed, probability of being left-handed. Probability of wearing glasses. Okay, if you wear glasses, we got about 8 people here wearing glasses. I just did a quick search. maybe it's less than that. I think 6. So I have 22 students, 6 of them are wearing glasses. Find the probability of wearing glasses, 6 out of 22. Find the probability of not wearing glasses. Okay, so if the word not appears, that's a complement. So if you see the word not, probability of wearing glasses, the complement to that is probability of not wearing glasses or no glasses. You might see the word no or not. So these are complements to each other because the sum of those two things equals the whole. The sum of wearing glasses and not wearing glasses equals the entire group. Okay. All right, 3.1. Try to do some homework. Try to get it done now. At least you have time to do probably about half the homework. So I'm going to give you about 30 minutes. Try to get through some of that. You need to, if you got your computer, you can type it out. That was really cool. A lot of people type their homework. So it simplifies some things for you. So yeah, 30 minutes and the page. I erased the page number. Page 100. Are we on page 100? Yeah, 140, 2 through 50 even. So yeah, just title that page 140, 2 through 50 even. Sounds like a lot of problems, 2 through 50. Holy cow, 2 through 50. But the problem set is pretty long. I cut out a lot of problems. The problems go up to problem number 85. Okay, so we're not even getting to most of those. And some of the problems are like, find the probability of choosing a resident that's 15 to 29 years old. Okay, the answer is a fraction that can become a decimal. Find the probability of not choosing someone that's 15 to 29 years old. So you take the total number of outcomes, that's what you're going to divide by, and take the number of outcomes, divide by that. All right, go for it. Ready for some new stuff? Yeah. Not really. Okay. That's why I said today's gonna be a little tough. There'll be lots of new stuff, lots of new things to learn. The cool thing is 3.2 and 3.3 are kind of connected because they use the similar, very similar ideas. They use ideas of probability in terms of multiplication and addition of probabilities. So I'm going to teach this using a couple of different methods. I'm going to use a couple of examples. The example I'm going to use is actually problem 7 on page 152. And this is an assigned problem. And also I changed the homework. The homework on the syllabus says 5 through 19 odd. I changed it to 5 through 29 odd. Okay, I added some problems just for the sake of understanding. Because I don't know why I put 5 through 19. I think that was a typo, but page 152. Number 7. So this is taking a survey at a college. University of Oklahoma Health Sciences Department. They surveyed people and they wanted to find out, like, you know, what's going on in the nursing program. We need more male nurses, or we got enough of them, or we need more people to be in our program. Find some probabilities and use these probabilities to come up with some stuff. Okay, so I'm going to answer a bunch of questions about this information. And this is very similar to what I do on a quiz, what I do on the test. Given some data, answer some questions about that data. Okay, so find the probability of certain events occurring. So remember, probability of an event. This is a closed space. Find the probability of an event occurring. I'm going to calculate that probability using this information given. So find the probability of being male. How many males were in the study? So I'm gonna figure out, but probably, male, female, usually so around, 48% or something like that. He's around half or something like that. We're gonna find probably to be male, and they're in health sciences. So how many males are in the health sciences department? So I'm gonna just take the number of males in the health sciences total. Divided by 3,605. Okay, I'm not really concerned what the probability is. I'm not really concerned what the probability is because I can use the fractions. Okay, I'm more into fractions than decimals, but I can simply punch buttons in the calculator to find those numbers as decimals. Really easy to do. Okay, find the probability of being male. I can answer the same question, find the probability of being female in health sciences department. Find the probability of being a nurse in health sciences. Probability of being a nurse. There are how many nurses? There's 819 out of 3,605. In health sciences in Oklahoma, there's 819 total nurses. Okay, I'm not worried about these numbers in here when I'm asking these questions. So these are two different events occurring. When two different events occur, we have marginal probabilities and we have conditional probabilities. So the title of this section here actually is called conditional probability. Okay. Yes.
For the homework, it's 152 is for 3.2.
Yeah, so we're on 3.2 right now. So we're done with 3.1, so we're going to 3.2. But I'm giving different questions here. So these aren't the questions that are on the problem. The problem gives us different questions, but I'm going to get to those in a minute. I'm just using this problem as an example because I don't like any of the examples in the book. And I usually make up an example for this, but I decided not to today. So this one is useful. And the reason why is because this pops up in 3.3 as well. This question. It also pops up in the chapter quiz, I believe. So now I'm going to answer a conditional probability. Okay. So I'm going to answer multiple questions about this. So when you're talking about a conditional, under what condition is something happening? So what are the conditions? Well, what is happening? Okay. I'm going to use some notation here. And the notation pops up in these two rules. Okay. So this is a conditional probability rule. Whenever you see the word and, we have to understand the multiplication rule first. When it says and, that means we're going to multiply probabilities together, kind of like the fundamental counting principle. Okay. We're going to multiply these two probabilities together. Find the probability of event A and B. Find the probability of being male and a nurse. Well, that's probably being a male nurse. How many male nurses are there in the health sciences department in Oklahoma? There are 94 male nurses. Okay, you be male and you can be a nurse. There's 94 out of 3,605. Okay. So I'm going to teach what the conditional is first. I'm going to teach what this thing is right here, and then I'll teach the multiplication rule. Because that's kind of the method of being used. Okay. So find the probability of being male given that they are a nurse. So we saw probability of being a nurse is 819 out of 3,605. Probability of being a male given that they are a nurse. So that little thing right there. Didn't play basketball. I make it half the time. All right. Nurse. This means right here. This means given that. So the way it's written, this is event A. No, I think I have colors in here. All right. This is event A, this is event B. That's passes up. A comes first before B. So probably being male, given that they are a nurse. So being a nurse comes first. Okay, so that's kind of important. We're talking about nurses only. We're given that they are nurses. So we're only talking about this group here, the nurse group. And we're not talking about females and everybody else over here in the health sciences department, the 3605. We're only talking about nurses in this problem. Okay, so that's our condition. Our condition is that you're a nurse. So the total, how many total nurses are there? That's what we're gonna divide by. There's 819 total nurses. And how many of those nurses are male? 94. And I figured that out. That's 94 out of 819. About 11% of nurses are male. Okay. That's a different way to say the same conditional under that condition. That's 11%. Maybe I'll write it as a decimal, 11.11. But if you calculate the total number of males in the health sciences department, 1198 out of 3605. 33. Okay, so finally, I'm the director of the College of Health Sciences at Oklahoma University. I see that 33% of our students are male in the health sciences department. I'm going to use this conditional to say that, well, only 11% of the nurses are male. Okay, then there's a disconnect there. Okay, they're not equal. If those two numbers are equal, then the probabilities are called independents. They are independent probabilities. And it's actually the very first definition that you run into in conditional probabilities. The two probabilities are independent. Probability of A are probability of B given A equals probability of B. Probability A given B equals probability of A. I just had a bunch of stuff there. Not really that big of a deal, but it just says that if these are equal, then the events are independent. You see that word right here. Events are independent. We'll be able to prove independence and we'll be able to prove dependence today. In a little bit, but that's how you calculate a conditional probability. A different probability would be this. One probability of being a nurse, given that you're a male. That's a completely different probability. Okay, we're not talking about nurses only, we're talking about males. All the males in the health sciences department. So health sciences, in the health sciences, there's nutritionists, there's doctors, there's also nurses. There's a lot of people that work in health sciences in the University of Oklahoma. So this is asking a different question. Given that you are male, so we're only talking about males. We're only talking about this group here. Okay, so we're going to figure out the total number of males in health sciences, which is 1198. And how many of those are male? Or 94. So talking about all the males in the health sciences department, 94 out of 1198. 7.8. Okay, much smaller amount. There's a smaller number here. Why is that? Why is that? Okay, so you're talking about all the males in the department. All the males in the department. A smaller percentage of them are nurses. Okay, so that means there's a lot more people in other fields. Does that make sense? Okay, so it doesn't add up. They're different things. They're talking about completely different things. They look the same, they sound the same, but they're not close. Okay,
You said the first one was condition probability and the last one is what?
this is a conditional probability. So this line means it's a condition. Under the condition, given that a certain event occurs, so this event comes first, this event comes second. So they usually use A's and B's for probability for those.
So if point 33 not equal with point 11 is the dependent.
Right. So that's a good point. What's the difference between these two? So that's another rule. I guess I'll address that because it's on page. I mentioned it. Page 148, the independence and dependence. If the probability of A given B equals probability of A, the two events are independent. So that's from page 148. And if I switch the A's and B's around, it the same thing would be probability of B, given that the probability of A equals probability of B, the two events are independent. So what Hung said was, if that's not true, then the events are dependent. Exactly. They're one or the other. If this is true, the events are independent. If this is not true, the events are dependent. Okay, so I'm going to use the notation that we did here. This that we did here. I'm just going to use the letters. The probability of being male, given that they are a nurse, does that equal the probability of being male?
No.
Okay, are they equal? So probability of being male is event to A, that came first. Okay, male. Probability of being a nurse, event B. If they're equal, then we're gonna say, does this work? Probability of being the total number of nurses was 819. Probability of those being male is 94. Probability of being male is 1198 out of 3605. If those are equal, then the two events are independent because it satisfies that rule. Okay, they're not equal. I see 33 and 11 are not equal. Therefore, if they're equal, they are independent. These are not equal. So the two events are dependent. They depend on each other. And we can't decipher independence and dependence based on our knowledge of what those things mean. We decipher that based on the rule for probability. Find the probability of being a female, given that they are a non-nurse. So let's try that one. Find probability of being female. I'll put it up here, given that they are non-nurse. So see if you can do that real quick and talk it over with somebody, if you can. Find that conditional probability. Again, we divide it by the total. This is the total. Some people think of this line as division. Does that make sense? The line means divide by that number. But when I divide, I'm divide this, think of this as division, divide by the number of non-nurses. Which is 2786. And how many of those were female? 1104. Sorry, what's that? Or 1682, yeah, thank you. 1682 divided by 2786. This would be a different probability if we did 1682 divided by 2407. That's probability of being a non-nurse, given that you're a female. Okay. So now I'm going to get into the multiplication rule. Okay, multiplication rule. Using this idea. The multiplication rule applies if we have dependent and independent events. So these are the rules. Find the probability of being male and a nurse. So I'm gonna do it right over here. I actually have to use the multiplication rule for dependent events because I just proved that the two events are dependent. Does that make sense? So I'm gonna use that rule up there. To find the probability. Find the probability of being male and a nurse. So this is event A, that's event B. M is A, N is B. Okay, that's probably being male, probably being a nurse, given that they are male. Again, these two events are dependent because I just proved it. And I can prove it using other methods. There's many ways to do this. All right, so let's do the calculation. Find the probability of being male. That was 1198. 1198 divided by total number of males, 3605. How did I know total? Because this right here says find the probability of being male. I'm only talking about males out of the total amount. Okay, how many males are in the population? So this is really cool how this works. Divide by the total number of males. How many total males are there? There's 800. Did I write the right number up there? On the probability of being male.
94 and 1198 divide on the bottom.
On the probability of being male, 94 and 1198. So like I said, this is really cool because watch what happens. I like the fractions. You could do decimals. You could write that number as a decimal and write that number as a decimal and multiply them together. But watch what magic math does for us with fractions. Remember that whole cross-canceling deal in I think it pops up in like junior high. All right. These two events are dependent. Find the probability of being male and a nurse. That's 94 out of 3605. Let's take a look at it. 94 out of the total population. Does that make sense? Find the probability of being a male nurse. Well, there's 94 male nurses in all of the health sciences department. Does that make sense? This male and a nurse is 94 out of 3605. They're equal, therefore these two events are dependent. If you try to prove that two events are independent, or you try to use the multiplication rule for independent events, watch what happens. I'm going to use probability of being male and a nurse. And I think that these two events are independent. Well, I already know that the answer, I already know that this, find the probability of being a male nurse is 94 out of 3605. If these two things are, is this equals that, then the two events are independent. I'm going to use the multiplication rule. Probability of being male was right here. 1198 over 3605. Probability of being a nurse. Probability of being a nurse. That's 819 out of 3605. Multiply that out, and you'll find that those are not equal. I can figure this out. I'll do it real fast on my calculator. 1198. I got 7.5. That's 7.5. On the probability of being a male nurse. All right, is 0.11. This is 7%. This is 11%. They are not equal. Not equal. Therefore, dependent. They're not independent, they are dependent. Again, it's one or the other. I used the multiplication. This is the multiplication rule for independence. I tried this one. I tried to see if it would work, and it didn't work.
The other one.
Oh, up here? This was the dependent. This one was up here. Okay, I drew the arrow right there. All right, so I tried the dependent rule, it worked. I tried the independence rule, did not work. Good thing I have another example over here, because that's a little confusing, isn't it? It's kind of tough to wrap our brain around. Use the multiplication rule. I got some cards right there. I'm not going to do magic unless you think probability is magic. Okay, there are jacks and spades, so I want to find the probability of getting a jack and a spade. Well, let's use that multiplication rule. Let me write it right over here. Find the probability of getting a jack and a spade. So I'm going to use this up here. And it's weird that this multiplication rule actually, both of them work. Both, this is not independent nor dependent. Okay, it's just because it's a classical probability. This is an empirical probability. Classical probabilities, both things work usually. But I'm just going to apply the multiplication rule. Find the probability of getting a jack and a spade. Find the probability of being a jack. There are 4 jacks down here. Find the probability of being a jack. And multiply by the probability of being a spade. So what's the probability of being a jack? Okay, there's 4 of those. And I can see them right there. 1, 2, 3, 4. Find the probability of being a spade. Okay, there's 13 of those. I put them all right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 13 of those. There's 13 of every suit in a deck of cards. Ironically. And if you didn't know, 4 times 13 is 52. And again, cancel. That's 1 out of 52. Find the probability of getting a jack and a spade. That's the start. There's only 1 of those. There's 1 jack of spades. Okay, 1 out of 52 cards are jack of spades. Does that make sense? It satisfies the rule of multiplication rule right there. I multiplied and it worked. One card is a jack of spades. Okay, so that's using the similar idea of multiplication, using the multiplication rule. But the multiplication rule, sometimes it depends on if the events are independent or dependent. Okay, so I'm going to tell you how you know if you're given a fixed sample size, the probabilities are going to be dependent. That means probabilities will change if your sample size is fixed. If you're given a probability out of an entire population, your probability is going to be independent. Okay, so an easier way to understand this would be if I gave you a number, like I said earlier, 6 out of 22 students wear glasses in this class, wear eyeglasses. Okay, 6 out of 22. Find the probability of randomly selecting 4 people that wear glasses. What's the probability of that occurring? So I could use, it's a fixed sample space. Okay. It's not a proportion. If 6 out of 22 is a sample, then I'm going to use those numbers and the probability is going to change. What if I said 20% of the population wears glasses? Well, now I'm talking about 2 events that are, I'm going to talk about find the probability of finding 4 people. The events are independent. So if you're given a percentage of a population, those probabilities are going to be independent of each other. If you're given a fixed number of an amount, those probabilities will be dependent. So this is a different, I'm going to use this example because there's some problems like this. I'm going to keep that over there. I'm going to erase all this. Unless you need a picture. Actually, there's a table in the book. I'll refer to the table in later today. So all of these are in the book in a nice little table that I'll refer to. Okay, so I need an example now. I talked about eyeglasses. Okay. 6 out of 22 wear glasses in this class. Find the probability. Well, I think I said 4. Find the probability of randomly selecting four people that wear glasses. So I can answer a bunch of questions about this. Using complementary events and using the multiplication rule. Okay. So I have 4 people. I'm going to use, like I did earlier, there's 4 people. I'm going to use multiplication rule. Okay, find the probability that 4 random strangers actually wear glasses. So I'm going to randomly select. I have my sheet. Remember how I randomly select people? I can use the calculator, or I can use the table of random digits to randomly select people in this class. Okay, so I randomly select a number. Let's say it's number 7. Okay, you hide it. Is that right? Okay. She's not wearing glasses. That's a compliment. What's probably getting 4 people that wear glasses out of 6? So that's the question I'm trying to answer right now. Randomly pick those people. It's going to be a really small probability that 4 people are going to be wearing glasses if I randomly choose 6. So here's how you calculate the probability. On the probability that the first person is wearing glasses. So how many people are in the room? There's 22. And 6 of them wear glasses. Find the probability the first person wears glasses. That's 6 out of 22. Because there's 6 people that wear glasses out of a room of 22 people. Okay, the next person, I selected my first person wearing glasses. My second person has to wear glasses. This is a dependent event. Use the multiplication rule for dependent events because I already chose one person that wears glasses. How many people left wear glasses? Okay, it changed. There's 5, okay. And how many people are left in the room? 21. Thank you. So I had to subtract 1 from that. Okay. This is kind of like the replacement and without replacement thing that we did earlier. Remember if the numbers repeat or if the numbers do not repeat. Remember that? So this is like numbers with no repeats. Okay, the numbers are not repeating. So we're not repeating people. Next would be 4 out of 20. Next would be 3 out of 19. So I multiply all those out, I would get my actual probability. The probability changed. Does that make sense? So that's when events are dependent. This is like if I have a deck of cards, okay, there's a deck of cards. Find the probability of getting a king and then getting a queen without replacement. So I pull a card out of the deck and I pull it out and it's a king. I take it out of the deck. Find the probability to get a king and a queen. So that's 4 out of 52. I'm probably getting a queen. So how many cards are left? There's only 51 cards left because I took one out. So 4 out of 51. That's actually example, I think it's example number 1 in the book. So if you go through and you read the book, when in doubt, read the book. Example 1 in the book talks about getting a king and a queen in the deck of cards. Okay, that's conditional probability. These two events are dependent and we multiply, we use multiplication rule for that. Okay. That's dependent events. Notice I got a fixed number, 6 out of 22. I selected the people in this room. Okay. 20% of the population that's about 1 out of 5 wears glasses. Okay, this is an estimate. Don't go to Google and look it up and then tell me that I was wrong. It's always changing. It's an ever-changing probability. 20% of the population wears glasses. Find the probability of randomly selecting probability. Can I spell? Randomly selecting 4 that wear glasses. This is probably going to be a little more likely, but the probability is calculated a little differently. I'm going to use the same method. 4 people in the book, they do 3 people. You're going to randomly select 3 people. You're going to randomly select 6 people. So that's how many different ways that an event will occur. Okay. So I'm going to do my same thing. I'm going to do my boxes here. I'm selecting 4. Okay. The box represents each person that I randomly select. Here's my box. Okay. Find the probability of picking a person in the population of everyone in the world that wears glasses. Okay. 20% wear glasses. So that probability is 0.20. Let's select another person in the world. Okay, am I going to remove that person from the population of 7 billion people? Okay, 7 billion. Okay, 20% of 7 billion. I'm going to subtract 1 now. Still going to be about 7 billion, right? Kind of like the odds of winning the lottery. Okay, play $1 for the lottery, or play $2 in the lottery. The probability is pretty much the same. It's not going to change. So 20% of the population times 20% of the population times 20% of the population times 20% of the population. I ran this like 4 people. I just multiply 0.2 times 0.2 times 0.2. In the book, they use blood types. Okay, type B positives, type A positive, and I think the question I put on the quiz is type O blood. Okay, 5 random people are selected, unrelated. What's probability of being type O blood? And I just use that because I'm type O blood. Probability is about 30% of the population is type O, about 30%. Find the probability that 5 random people are type O blood. Well, that's pretty unlikely, isn't it? It's really small. But the probability is gonna be 0.3 times 0.3 times 0.3, 0.3 times 0.3. A shortcut to write this would be an exponent, 0.2 raised to the fourth power. Probability of 5 people being type O blood is 30% raised to the fifth power, because there's 5. Okay. So they got, again, problem 27 is B positive blood, 9% of the population. A positive blood, 31% of the population. Then they got ART, assisted reproductive technology, 45% of the population. Okay. Then there's a casino problem. Casino problem is pretty cool. I skipped that problem. But they're similar to using these percentages. So there are 2 different types. There's actually 3 different types of problems. There's a problem where you'll get a table. There's a problem where you get a number, okay, a fixed number. There's a problem where you get a percentage. Okay, so there's 3 types of problems that you're going to see here. I can use the same idea with the lottery. Remember we did the lottery problem? Find the probability of winning the lottery. Well, instead of doing 75 times 74 times 73 and divide by 1, I could have did 1 out of 75 times 1 out of 74. Probability of getting the first number. That's probability of getting the second number. Oops. Use the multiplication rule. It's dependent events. The probability of winning a lottery would be the same thing that we used earlier by using the fundamental counting principle. It mirrors the multiplication rule. Yeah, win the lottery. Sound good? Kind of went through a lot there. There's going to be more. There's going to be more. Don't worry. This is the multiplication rule. We got the addition rule where we're just going to add probabilities together. Right now we're multiplying probabilities. The addition rule that we'll do later is adding, we're doing plus. Okay. But I'm going to use that example to talk about plus adding. Sounds good. Let's go. 30 minutes. Takes time. Try to get on each problem type. We should be good there. Oh, and the homework is right here. It's 5 through 29 odd. So make sure 5 through 29, not 5 through 19. That's on the syllabus. Oh, I changed it already on the syllabus. So if you print it, if you ever printed it, make sure you change it to 5 through 29. Okay. All right. One more thing. But wait, there's more. The probability of something occurring, an event occurring, is calculated, and it's always the number between 0 and 1. So once we get that probability, we're solid, it's between 0 and 1. Make sure if you end up with a number above 1.0, like sometimes you'll do calculations, you'll punch numbers on the calculator, you get like 1.25 or something like that. You know you did something wrong. Okay, just pointing that out right now. If you get a probability below 0.05, if you get a probability, your probability is less than 0.05, probability of the event is less than 0.05, then that is considered an unusual event. Unusual. So that question pops up. It says, if something happens 3% of the time, that's unusual. If something happens 1 out of a million times, that's unusual. If something happens 4.2% of the time, that's unusual. If something happens 20% of the time, not unusual. Okay. So I use the normal distribution. We'll get to that later in chapter 5, but normal distributions, 95% of the time you're driving on the freeway between 65 and 75, right? 95% of drivers drive between 65 and 75. That means 5% of drivers have speeds outside that range. Anybody driving below 65, that's unusual. Anybody driving above 75, that's unusual. It doesn't happen very often. 5% of the time, unusual events. Okay. So we'll talk a lot more about that with normal distributions. The last thing is this idea of at least one. So there will be a question and it pops up here in some of these problems. Find the probability that at least one of these events occurs. Okay, with the coin toss, find the probability of getting at least one heads. That's probability of getting one or two or three heads. That's at least one. Well, to calculate it, you find the probability of not getting any heads and subtract from one. Let me show that the heads again up here. I'll do it over here. So remember heads, the sample space. I'll do it all over again. Heads, heads, heads. I'm gonna write really small this time. Sorry. And then we got tails. All right, so there are 8 outcomes. Find the probability of getting at least one heads. There's at least one. There's at least one. There's at least one. There's at least one. There's at least one heads. There's at least one heads. There's at least one heads. So there's 7. There's 7 ways for it to get at least one heads out of 8. Or I can find the probability of not getting heads and subtract from 1. It's a complementary event. So whenever you see this at least one, that's 1 minus the probability of none. So again, using this example here, find the probability of getting at least one head in a toss of 3 coins. Well, that's 1 minus probability of none, which is 1 minus probability of 1 minus 1 over 8, which is what I just counted, 7 out of 8. Let me divide this up here. Okay, there we go. Again, it's tight over here. So I got 7 out of 8. 7 out of 8 of them are heads. That's the probability of getting at least one heads. Instead of counting how many ways this can occur, we do the 1 minus none. So in this case, find the probability at least one person wears glasses. Well, that's 1 minus probability that nobody wears glasses. We found the probability that 4 people wear glasses. Found the probability that none of them wear glasses. So that's the complement to each of these and subtract from 1. Okay. So 1 minus none gives us that probability. That's something that at least one thing, that's a little more complicated, but when you get to those later problems, it's popping up. A couple people asked about it. I think it's problems 23 through 28. Ask about that. Okay. So when you get to 23 through 28, you're going to encounter the probability of at least 1. Okay. 3.2 again. We'll go about 10 more minutes. Keep working for a few. Again, reminder, take your break if you can. All right. So we got one last thing to discuss, and I get you on your way. It's actually 2 parts. There's 2 more probability rules. And in fact, all of the rules are on page, well, not most of the rules are on page 161. So if you want the probability rules, refer to page 161. Page 161 has the classical probabilities, multiplication rule for dependent and independent events, complementary events. And what we're going to do right now is called the addition rule. In the addition rule, we're going to do addition. We're going to add probabilities together. So I'm going to give you some examples of probabilities that we're going to add together. If I'm adding probabilities, that means we can be one thing or another. So with the addition rule, there's two types of addition rules. If two events cannot occur at the same time, they're called mutually exclusive. So that's the first definition, mutually exclusive. Two events cannot occur at the same time. So in a deck of cards, the deck of cards example. And use deck of cards as an example. Find the probability of getting a 5 or a 9. 5 or a 9. Well, that's probably getting a 5. Plus probably getting a 9. Get a 5 and get a 9 are called mutually exclusive events. They cannot occur at the same time. Get a king or an ace. Okay, empirical probability. Find the probability of driving to school or walking to school. Okay, did you drive here or did you walk here? It's one or the other. Find the probabilities. I'm going to add those together. Are they all the probabilities that are out there? No, because you can ride a bike to school, you can ride the bus to school, you can carpool, right? You get dropped off. There's all kinds of different probabilities. Find the probability of doing one thing or another. So when we do that, those two events are called mutually exclusive. This is called, if two events cannot occur at the same time, we're going to use the addition rule. And we see the word or. The word and signifies the light bulb goes on and bing. That's multiply. It says or, light bulb goes on, bing. But we're adding. We're going to add. So the probability of A or B equals probability of A plus probability of B. That's if two events cannot occur at the same time. If they can occur at the same time, the events are not mutually exclusive. So if they're not mutually exclusive, it's kind of like independent or dependent thing cannot occur at the same time. So two events that are not mutually exclusive, they cannot occur at the same time. So the addition rule doesn't apply. Well, it does, it's just a modified addition rule. The probability of A or B equals probability of A plus probability of B minus probability of both. I'm just going to use the word both. It says A and B. Both A and B occurring.
So for the top one, put the same thing as the bottom one, cannot occur at the same time. Is it the same as?
Oh, thank you. Can occur. Oops. They can occur at the same time. I'm going to give you a couple of examples of this that we already saw. Sorry, thanks. Good catch. Two events that can occur at the same time, they can happen together. So I used the riding the bus and driving to school. Okay, you're gonna ride the bus here or you're gonna drive here. Okay, one or the other. Can't do both. Okay. wearing a jacket or wearing a sweatshirt. Okay. In that case, can you wear both? Yeah, I've done it many times through March, April, and May. It was super windy out there. I wore a sweater with a hood, sweatshirt, and I wore a jacket over the top. Okay. So if you can do both, if you can do both, find the probability of wearing a jacket. We got people wearing jackets. Find the probability of wearing a sweatshirt. We got people wearing sweatshirts. Hey, we got people wearing both of those. Okay. Can occur at the same time. You can do both. Okay, so the example would be here. But if the events cannot occur at the same time, find the probability of being a nurse or a non-nurse. You're gonna fall in one of two categories. So when they come out and do the survey and they ask you, are you a nurse or a non-nurse? Okay, so what's your major? Is it a nursing major? So you're gonna pick a category. You're gonna pick one. Okay. So where do you fall? Okay. So that's two events that cannot occur at the same time. You're gonna be in one or the other. Find the probabilities. We're just gonna add these two together. Okay. Two events that can occur at the same time. That's like your gender and what your major is. Okay. So let's do that one. I'm gonna look at not mutually exclusive. Find the probability of being a nurse or male. Can you be a male nurse? Okay. You can be both. They can occur at the same time. So those events are mutually exclusive. So I gotta use that rule. I gotta use that rule right there. That's probably being a nurse. That's probably being male. That's probably both. Okay, I'm gonna use fractions. I'm gonna use fractions for this, and then I'll go into the decimal. Okay, so just so you can see it. Probably being a nurse. A19. We use these numbers already. Should be familiar. 3605. Probability of being male. Okay, how many males were there? There's 1198 out of 3605. Minus probability of being both. You're a male and a nurse. Okay, that was 94. So I don't have to use the multiplication rule here, just because it occurs there. And whatever I get is my answer. Okay. Probability of being male or a nurse. Okay, it's right here. So if I just add 819 and 1198, I add these two together to get 819. I add these two together to get 1198. Well, I count this number twice. Males, I counted them in the male group. Nurses, I counted those 94 people that are male nurses in the nurse group. Okay, count the nurse group, count the male group. I counted 94 twice, therefore I have to subtract the 94. Okay, because they got counted twice. And you can figure out what that decimal is. Again, this is the case where a lot of times you'll end up with a number above 1 when you're doing the calculation. If you're doing the addition rule and you just simply add two numbers together, 0.9 plus 0.8 is 1.7. If you get a number above 1, okay, you should be like, okay, I did something wrong. I gotta subtract. Okay. So last example, probability of a jack or a spade. We did the jack and the spade, the jack of spades. Remember the jack of spades, there's one of those. I'm probably getting a jack or a spade. Well, I gotta do the same thing. Probability of jack plus probability of spade minus probability of both. And I showed them right up here. On the probability of getting a jack. 4 out of 52. Does that make sense? I'm probably getting a jack. That's 4 out of 52. Plus probably getting a spade. How many spades are there? There's 13 spades. 13 spades. minus probability of getting a jack of spades, 1 out of 52. If I just simply add these together, find the probability of getting a jack or a spade, one or the other, in the deck of cards. I pulled the card out. Okay, there's 4 jacks, there's 13 spades, that's 17. But if you look up here, there's only 16 cards. Because the jack of spades is counted twice. Okay, this card right here, the jack of spades, it is a jack. It is also a spade. So it's both, right? So we count it here, 4 out of 52, 13 out of 52, we count it twice, therefore we have to subtract 1 time. 1 out of 52, okay. Again, that's all of these rules are on page 161, so that's the page that I would bookmark. That's the page that I would take a look at. When I want to know which rule to use. Okay, page 161. Sound good? Yay, bravo. All right.